Yeah, welcome back to our new session of electronic circuits theoretical concepts. And for today, uh, let's investigate about dependent sources in circuit analysis. So today we are just dealing some exercises. Okay, we are trying to analyze the circuits having dependent sources. And as I have also specifically look, you can check out the in the circuit the dependent source. It is represented by a diamond symbol. All right, and for current there is arrowhead, whereas for the voltages you have the positive and the negative. You will see the types of dependent sources. All right, and dependent sources are those sources which are dependent, or which are related with other sources. Okay, which are not self independent. Okay, so these are dependent sources, and you guys can check out that this is a independent source because it doesn't relate with other kind of sources. All right, but this dependent source is related with other sources. That means you can check out their ix. The value of a dependent source is dependent on this variable, that is ix, right? And ix is somewhere else present here. Okay, so this dependent sources is totally dependent on this current ix. Alright, so now let's try to solve this kind of circuit. And here it says that compute V. So what we have to do is we have to compute a V here. Okay, that is a voltage. So what can be done here to compute a voltage? And having the circuit having also a dependent source, what can be done? How can we solve a circuit with dependent sources then? So you can check out. Okay, for example here you guys can also use, okay, let's before going to the solution, let's think critically what can be done. This is something like there is a top node and a bottom node, so I think Millman can be used here, right? So by using Millman I can just find the voltage V, because the voltage is same through all the circuit elements. So by this means I will first try to, without any knowledge of how to use dependent sources, I will try to solve using Millman. Okay, and I try to find V. And what happens? Yeah, you will get some kind of result, but there is also another variable, circuit variable, that is ix. Okay, because the voltage here will be this resistor multiplied by ix and times this one. So there are some certain situations here. So by using Millman I will get, okay, so also in the exercise you can check out here, by using Millman I get some certain situations, like I get the current here, the addition summation of all the currents at 10 by 2. You guys can check out the voltage divided by resistor and 2ix, that is the same dependent source. So the basic idea that I want to show you is, like, also for the Millman works for dependent sources. So dependent sources, the voltages or current of the dependent source also can be added as a source. Okay, they also act as a source. That means not they also act as a source, but they can be also taken as a summation. The current or a voltage that dependent source contains can also be added. Okay, they can be added. And lastly, you just divide it by the conductance, and those are this one and this one, right? And lastly we get the value. Okay, and ultimately we get the value here. So this was the first concept. So from this circuit analysis I can just make you assure that you can also use Millman for dependent sources. Okay, and it works as a normal independent sources. But okay, so let's solve exercise number 2 then. exercise number 2, we also have to compute I, that's the current that's here. So what can be done here? As you guys see and check out that you cannot use millman here because there is a resistor between these two nodes here. And what else can be done? Okay, actually here is this is a dependent source that is dependent with current. You guys can just check out that is 4ix. okay, there is some printing mistake here. 4ix is here, alright, and it is dependent with this current that is ix. So if you check out, what happens is like from this junction you can find the current, and you can find the current here, right? And what happens is like the current here will be ix, and it's just going this side, so it will be like ix is flowing here, so ix minus 4ix, so it will be like minus 3ix. okay, but here will be also a minus, so it will be like the current will be something like 3ix. Then okay, what can be done here? ix here, I is here, 3a is here. So the basic idea is like if you also taking the node here, like the junction here, if you solve KCL, you can find that this current is a sum of 3 ampere and ix. So our ultimate goal is to find ix. So how can we solve it? Okay, for ix, to find the value of ix, so you guys can solve this circuit to find the ix. So what I have done here is, you can check out that I have just I tried to find millman. Okay, I just indicated this bipole to calculate the Thevenin equivalent circuit, so that I will just find the Thevenin equivalent circuit that consists of a resistor and a voltage source, or VThevenin and R equivalent. So getting VThevenin and R equivalent, I can easily find the value of ix, right? So that trick I am going to use here. So you guys can check out here, V, the Thevenin voltage V will be equal to R3, that is R3 is this 4, okay, and ix minus 3ix, ix minus 4ix, this will be minus 3ix, and this is R3, so R3 is 4, 4 3 is 12, so 12ix. okay, just printing mistake, just be careful about this ix. And after finding this one, like the Thevenin voltage, you have to find the equivalent resistor. So for equivalent resistor, you just divide the total current supply that is supplied from here, okay, divided with the voltage. So actually the whole voltage is provided. Okay, what you do is this ix just act as a external voltage source, okay, current source, okay. So it can be also, you just divide to get the R equivalent circuit, and that's it. You just get the Thevenin equivalent circuit, and substituting the bipole with the equivalent circuit. You can check out the figure just down below here, 4.2.2. and lastly we just calculate VAB, okay. So you can check out, guys, like VAB will be this one, and I substituted Thevenin equivalent circuit here, that is V and R equivalent. External current source is just ix is here, so, and then I find the Thevenin equivalent here, the millman here. Then similarly I find the result for I. Okay, first I find the millman, that is VAB. So after finding the millman for VAB, okay, I find the voltage here. So after finding the voltage here, I can also use KVL loop here in this loop, in this portion, or in this mesh. then immediately I can find the value of I, right? As you can see here, and I have also calculated here, and it was the result is 5.57 ampere. Okay, now before proceeding ahead for any newer exercises, I would just like to give you some key notes about dependent sources. Okay, always be careful that we cannot use the source transformation for dependent sources. That means you cannot directly use a source transformation. Like you guys remember, you cannot do a source transformation for here, for this particular circuit. Okay, I didn't did the source transformation. Okay, I just rather just decided to use the Thevenin equivalent circuit rather than doing the source transformation, right? Because doing the source transformation, the actual the behavior, or like it will lose its own behavior of being the dependency, okay, a dependent source. So to avoid losing the dependent behavior of a dependent source, you should not use the source transformation for dependent sources. Okay, rather you can use the Thevenin conversion. But we can use a source transformation for independent sources present in the same circuit. That means, but you guys can, if this is a independent sources, you guys can use or transform this like independent sources, but do not touch, okay, independent sources like dependent sources. Okay, so now the second key point is like while using Thevenin technique to analyze circuit with a dependent source, we do. Okay, so as you noted that for I use some Thevenin technique to analyze the dependent sources, right? But there is a specific, okay, procedure, or there are some steps that you should follow while using the Thevenin technique to analyze dependent sources. That is you should not turn off independent sources. Okay, do not turn off the independent sources which are dependent with the dependent source. Alright, because some independent sources may be turned off, but for example, if there are some dependent sources which are for example, let me see for the example. For example, if there are some, this can be turned off, okay, this 12 volt, because this is not dependent with this one. But there are some voltages which will be related with the dependent sources, that is Ix. Like if something is supplying Ix, like for example, there must be source, for example, any source which is supplying Ix to this dependent source, then the particular source cannot be turned off, okay. But other extra independent sources can be turned off, okay, except those which are related with the dependent sources. And after that, so after that, to find the Thevenin equivalent circuit, you have to follow just two procedures. That is, first is you find the V equivalent. Okay, before I was just telling that there was a trick, okay, to analyze with dependent sources. Independent sources are not turned off, because this situation occurs when you find R equivalent. Okay, alright, just be careful, because for R equivalent we turn off, you guys remember that we turn off all the independent sources to find the R equivalent. So but in case of a dependent source present, only the independent source which are not related with the dependent source is turned off, otherwise not, okay. So to find the Thevenin equivalent circuit, two procedures are followed as like before. As like before means as I have discussed before in my previous lecture, that for Thevenin equivalent circuit you just need two variables, that is V equivalent and R equivalent. So also here we find V equivalent, and we find V equivalent as for open circuit at the interface, where you are going to find like the terminal. And for R equivalent you are also going to find the uh, but in case of R equivalent, this is totally different. You are not going to turn off, you have to be careful about turning off the independent sources. Okay, and the second thing is you are going to find a short circuit current at the interface. The interface means the terminal where you are finding the V equivalent. So after finding the short circuit current, okay, you guys can immediately find out R equivalent by a simple Ohm's law, that is V equivalent by I mean V by IR, those implementation. Okay, now let's try to see this exercise. Okay, in this exercise 4.3, what we have to do is we have to just evaluate IR, okay, as a function of R1 using the Thevenin theorem. So what you have to do, guys, is you have to first try to find the Thevenin equivalent circuit. Okay, just turning off, I mean just making this as an open circuit. Just try to find the Thevenin equivalent circuit. That means first step is you have to find the V equivalent, that is just stated here. Look, it's just open circuit is created here. Then you try to find V equivalent, and how you find the V equivalent in this case? V equivalent here in this case can be found by using that this V equivalent will be equal to this particular voltage present here and this particular dependent voltage present here. Okay, voltage of a dependent source. So you use a KVL here. Okay, and you find V equivalent, and but I2 equals to I. How can you say that I2 equals to I? I2 equals to I because no current is flowing through here because it's an open circuit. So this current that is flowing here will only have a one part of flow, that is this one. It just flows through R2. It doesn't flow through this because it's an open circuit here. So just I2 equals to I, and lastly you find V equivalent. Okay, and for calculation of R equivalent you have to find a short circuit here. Okay, you have to just replace this open circuit with a short circuit and try to find a current flowing here, that's a short circuit current. And you guys to find the short circuit current here, it says that I short circuit is I, that is this current, minus I2. So it will be like this time the current flows here, so I just need to find the current flowing here, so it will be this I just use the KVL like KCL here in this junction and try to find the short circuit current here. Alright, and that's it. You guys can check out the diagram to calculate the short circuit current here. And after calculating short circuit current, it says that the I2 equals to 0. Okay, we try to equate here and we say that I2 equals to 0, so the short circuit current is equals to the current source here. And lastly we find the R equivalent, and we are done for finding the Thevenin equivalent circuit. Now lastly, to compute the IR, we just substitute the Thevenin equivalent circuit here. Okay, and the particular resistors is also placed here, and we just try to find the IR, the current through the resistors. And lastly we use this voltage division law. This can use voltage division, voltage division, then and divide by the resistor, so it will be the current. So I just use this trick here. Alright, and that's it. So for now let's go for the next exercise, and in this exercise you guys have to find V2. Okay, so for finding V2, what you guys have to be careful about is what is V2. Let's check out the situation here. And we have also dependent sources here, that is a current, dependent sources of a current, and but it is dependent with voltage here, so it's a voltage dependent current source. Alright, And for V2 the situation is like you guys can also similarly turn off this, or open circuit this and try to find V2. But before that, what I have done here is I applied Millman directly here so that I can find V1. And after V1, finding V1, I just use the after finding V1, I just use this. I just try to find V2, and V2 equals to just -4 5 V1. That is the it's just this one. Okay, the current flowing here, that is 5 V1 times this resistor. So current into resistor is a voltage. So similarly, by using this technique, I find V2 here. Okay, now for exercise number 5, you guys have to find V here. So to find V here, what is to be done is, okay, so you guys can first check out what can be done here. We cannot use Millman, we cannot do any kind of voltage division, such thing. Okay, and okay, the idea is like there is a situation like 8 ampere is here, Ix is present here, so I can find the current flowing through here by using this junction, using KCL in this junction. Then after finding K, this current will be equal to this current and times this current, okay, flowing through here, current, okay, and I try to use KCL in this junction. And then similarly you guys can check out the situation here. First Ix, the Iy, Iz, okay, Iy equals to Ix plus 8a, and Iz becomes 2 minus Iy, that is this 2 minus Iy. And similarly I try to use a KVL in this loop, that is A, B, C, D, A, and I get the similar situation here. And after getting the equation, I try to solve the equation, find the value of Ix. Okay, after getting the value of Ix, I try to find the value of Iz, and lastly, finally I get the V, because when I get Iz, I can immediately substitute by using Ohm's law, right, and get the value of V. Okay, now let's begin the exercise number 4.6. And in this exercise, what you guys have to do is you have to build a Thevenin equivalent circuit at terminals A to B. Okay, so in this terminal we have to build a Thevenin equivalent circuit. So how can you find a Thevenin equivalent circuit? The first point is you have to always find a V equivalent. Okay, so how can a V equivalent find in this terminal or in this interface? From this interface AB, current flowing through the resistor R3. Okay, actually I was trying to find the current flowing through the resistor R3, that is, this will be summed, okay, because this current will not pass through here, will pass through here. So this current shows the current, that is A caret plus Ix will be added and flows through R3. And after finding the current here, I can immediately get the V equivalent, that will be the current, total current times R3. Okay, and after getting the total current, I apply the KVL loop in this particular loop here, you guys can check out. And with the loop I get the value of Ix, because you guys know the voltage already here, the voltage already known is here. This will be summed, this two resistor R2 and R1 will be summed, and the same current flows through here. And that's how you get the value of Ix. And lastly you get the value of V equivalent, substituting all this value of Ix here, and also the value of Fe and R3. Okay, and now for calculating the R equivalent, you guys have to substitute the open circuit with the short circuit, okay, and try to find the current in that short circuit. And respectively we get the following here, that is, the current will be just as you apply the voltage division here, okay, that is the total voltage divided by the resistor, the particular resistor. And also be careful that whenever you substitute a short circuit here, uh, the resistor R3 will be nullified because it's parallel with the short circuit, and the current Ix will only flow through here. Okay, so when current only Ix flows through here, you can easily find the short circuit current here by summing Ix plus A, that is equals to HFE Ix, right? And that's the trick I am using here. And lastly, I find the R equivalent by V equivalent by I short circuit, that is I equivalent. Okay, now for exercise number 4.7, what you guys have to do, compute I, okay, for the sub that is donated by this box. Okay, find will be to 2 times Vx. What V equivalent Vx? Because V equivalent here is already, because if you guys check out, it will be V equivalent is equivalent to, like, it's equivalent to these portions, right? I mean, if you check out the voltage that is Millman, if you guys can see the Millman from here, then the voltage flowing through here will be equal to voltage flowing from here and the voltage flowing from here, right? Because this is totally it has no effect, because it is floating. Okay, no current flows through here, and there is no voltage source here. I mean, no voltage also flows through here, so it is nullified. So if you guys check out, the voltage will be just the V equivalent voltage will be 2 times Vx, and after getting this total voltage, we try to use the mesh here, and after using a mesh, it is a KVL here, we try to find the value of Vx. Okay, after finding the value of Vx, what we'll do is we can immediately find the value of V equivalent, that is 2 times Vx. Alright, so after that the second step is to find the R equivalent. So for finding the R equivalent, what you have to do is you have to check out, okay, like what can be done. So here what is seen is like 2 times Vx plus Vx equals to 0. That means this voltage plus this voltage will be 0 if you start using a KVL here, right? So inside this loop, the loop voltage, summation of a loop voltage is 0. So solving this equation, you also find that the Vx equals to 0. So that means this portion of circuit has no effect, and lastly we just remain with this resistor, that is 3 ohm, that is will be the R equivalent. Alright, and getting the Thevenin equivalent circuit, we just substitute the Thevenin equivalent circuit here. Okay, if you guys check out my previous circuit was this one, right? Because that was to find value of I, and typically first use value of voltage, and after finding the minimum voltage I try to find the value of I, that is using the Ohm's law, right? So now for exercise number 8, okay, what we have to do is like compute the equivalent resistance of the circuit, that starting from the terminal A to B. Okay, from this interface I have to find the R equivalent resistance. So but for this particular case, for finding equivalent circuit, you guys have to be careful that for finding equivalent circuit, okay, in a dependent source we also need a V equivalent, that is a Thevenin voltage. That can be also a Thevenin voltage if you start thinking about from this point of view, from this interface. And then also you have to find a I short circuit from this terminal, okay, and then just you have to just use the Ohm's law and try to find the equivalent resistor. Okay, so that's the same technique that I am using here, but for this time I'm using a different substitution, that is a voltage, like I'm substituting this with a test voltage and a test current. Alright, also this can be done. Okay, alright, you guys can also find immediately the Thevenin equivalent circuit, or a test voltage and test current is applied in the open circuit, I mean the open terminal. Alright, and by using this test current and test voltage, the solution was like, first I just equated that Vx will be equals to Vp, because if you check out from this portion, if you see the portion, this is a dependent source. So, and if you see see from the point of view of Milman, you can also immediately see that this particular voltage will be equal to this voltage, and in addition Ix, okay, will be equals to minus E times, because you guys also check out that I have just um, turned off the independent voltage source here, okay, because this has no contribution in this two dependent sources. They have no contribution, so having no contribution I can turn off this independent source. So I try to solve this circuit, okay, this portion of the circuit. In this portion of the circuit I try to find the value of Ix, and Ix will be just this value, this dependent source value, that is a voltage value divided by this total resistor present in the circuit. So similarly I find the value of Ix, and this value of Ip, okay, what can be the value of Ip now? The value of Ip is using a junction here, okay, using a KCL in this junction, the Ip will be the value of current flow from A, and also the current flow here, that is R2. So R2 will be something like the total voltage, that will be the Vp divided by R2, the current flow here we find here, okay, and times this current, HFEIX for A, that is the value here, as you can see here, for A, HFEIX. Alright, for after finding the value of Ip, now the R equivalent is very easy, that is Vp by Ip, okay, that was just the test voltage and test current. This is just like finding the Thevenin equivalent circuit, Thevenin voltage, and dividing it by the I short circuit. Alright, now for exercise number 9, what you guys have to find is evaluate the Thevenin equivalent circuit at terminal AB. So for finding the Thevenin equivalent circuit for terminal AB, what is done here is use the similar technique. We can say that the equivalent will be like, you start taking the loop here. This V equivalent will be just mu Vz, okay, divided by the R by R plus R. So what is done here is R times R divided by R plus R is like the voltage in the R, okay, is divided by this voltage source, okay, dependent voltage source, because what you see is the V equivalent can be equal to the voltage present in this resistance R, right? So if you just solve this circuit, what you can find is the voltage division is done from this particular dependent voltage source with these two resistors, that is, and only one division is taken. Alright, and after this first equation, that is equivalent is equal to this particular value, I can also use the KVL at the loop outside here. So after we find the KVL here, and we also try to find the value of R here, okay, and we try to equate it here, and we try to find the value of Vg. So Vg of value is obtained, and lastly we obtain a value of V to the value that is substituted, okay, and you can check out here. And lastly we calculate the short circuit current, because we need to find also the R equivalent. So the short circuit current, verify this nullified, so the whole portion of this is nullified. So we just have this, the contribution of this dependent source, voltage source, and just we use this voltage source to find the value of current, and because this voltage source divided by this resistor present V equivalent by I short circuit. Alright, here we also similarly use the test voltage and test current here. Alright, for simplicity, then what it states is like the I try to find I try to apply KCL in the node C, so that means like this 2ix plus this 2ix and this IP 2ix plus this IP is equal to ix, right? So and I try to find the value of ix, that is equals to negative of test current, and lastly we use KVL at the loop, and we also use the KVL here, and it says that we use the KVL here, okay, and we say that the test voltage is equal to the this voltage plus this voltage, right? And lastly we solve and find the test voltage and test current and substitute with the R equivalent, that is equal to the test voltage divided by test current. Alright, and we find the respective value. Alright, this was just about the dependent sources. So guys, just be careful about all the tips that I have given for in case of the dependent sources. What are the situation that you should follow, or what are some important procedure you have to follow while finding the dependent sources and using Thevenin equivalent in case of dependent sources, and also using the transformation and closing the independent sources. So this kind of concept that I provided here will be very helpful if you try to solve this kind of dependent sources, okay, circuit with the dependent sources. Alright, so I will be back with the next topic in the new session. So thanks for listening.